Hello, I'm David Lee with the Virginia Asphalt Association, and this is Chapter 3, Components of Asphalt Concrete Mixtures for the Asphalt Plant Level 2 class. Learning objectives for today's module are: we need to understand what materials are used to produce an asphalt concrete mixture. What are the physical attributes of an asphalt concrete mixture? And then what types of asphalt mixes and binders are typically used in Virginia? And then the basic aggregate and asphalt properties. And lastly, become familiar with the most common asphalt concrete volumetric terms. So first, what materials are used in asphalt concrete mixes? Well, first and foremost, we have our asphalt cement or our binder. As you see in the bottom right-hand corner, it's a liquid product. It takes up about 4 to 6% of the total mix by weight, or 10 to 12% by volume. Again, if you think about weight versus volume, the product of asphalt concrete is put together with the aggregates and the binder, and it has air in it as well, so it's going to take up volume. That air takes up a volume. So 10 to 12% of that mixture is asphalt binder. It binds the aggregate particles together. We want them all to stick together, so that asphalt cement or the binder, that's the glue. That's the glue that holds your mixture together. And you need it to provide cracking and rutting resistance. So those binders are actually specifically formulated to help us avoid that cracking that can occur over time, and certainly avoid rutting in our mixes. And we always have to keep in mind that a percentage of that may come from our RAP or our RAS. RAP being the recycled asphalt pavement, RAS being recycled asphalt shingles. We have a little bit of the recycled shingles in Virginia, but for the most part, almost all of our mixes have some percentage of RAP. We also have aggregates in our mixes. They're about 94 to 96% by total mix weight. So again, 94 to 96% of that mixture is aggregate. So again, if you take that asphalt we had earlier that was 4 to 6%, so if you add 6 to 94, you get 100. If you add 4 to 96, you get 100. So now you have 100% of your material by weight. And the aggregates take up about 75 to 85% of the volume. Our fine aggregates, that's the small aggregates obviously, and those are the material that passes the number 4 sieve. So it has to be smaller than the number 4 sieve. The coarse aggregates, those are the ones larger than the number 4 sieve. And then lastly, again, just like it was with the binder, we can get our aggregates also from our RAP or our RAS. There is a percentage of those in our RAP, obviously, because it's a recycled product that came from either our pavements or from our shingles. So let's talk about the SUPERPAVE binder system. And they have a nomenclature for that. The binder naming convention is that PG, pound, X, dash, at symbol. So we'll go down those real briefly. PG, that just tells you that it's performance grade. It's a performance graded asphalt. VDOT went to performance graded with the SUPERPAVE system 20 years ago. That pound, that is the temperature in degrees Celsius, the maximum average temperature for 7 days the pavement is expected to experience. In most cases in Virginia, it's going to be a 64. Occasionally you'll still see a 76 used, but almost all of ours are base asphalts are based off of a 64. So it's 64 degrees Celsius, as it has to be. That's the maximum temperature that it'll experience over a 7-day period. Then that X, that is the traffic loading that the pavement is expected to experience. We have an S, an H, a V, and an E. S is for our lower volume roads, H is for our moderate, V would be for our very heavily, which Virginia doesn't use much, and then E is for our extremely loaded, like our interstates. And then you have the at symbols. That's the temperature in degrees Celsius, the minimum 1-day temperature that the pavement is expected to experience. For example, a minus 18 would mean that it's going to experience 18 degrees, negative 18 degrees Celsius as your minimum 1-day average temperature. All binders certified by Virginia Asphalt Acceptance Program, and VDOT contracts designate the binder to be used and the binder grade to be used when it's combined with both a RAP and a RAS. So Two of the most common binders that are used in Virginia are the 64S-22 and the 64E-22. You'll see that to a lesser degree the 64H-22, and that is because the wrap that can be used in our mixtures can take a 64S-22 and make it into a 64H-22. So in many parts of the state where we have a lot of wrap, you'll see 64S-22 used a lot. Some parts of our state where they don't have a lot of wrap, they'll have to use the 64H-22. But again, we use that 64E-22 for our heavily trafficked roads like in our interstates. So that S, again, is a soft binder. It's used on the lower traffic levels. H is slightly harder. It's used when you have used with more trucks. V, again, not used a lot in Virginia, but it's a stiff binder used for heavy loading. And then that E mix, that is the binder that's used for extremely heavy truck traffic like we see on our interstates. So now let's talk about our SUPERPAVE nomenclature for our pavements themselves. And VDOT convention for mixed naming, again, is using those same types of letters and numbers. We have that XX dash pound symbol with a dot, pound symbol Z. That XX designates the type of the mix. So we have an SM, an IM, or a BM. So that's a surface mix, SM. IM is an intermediate mix, and BM is a base mix. Our pound symbols, they designate the nominal maximum size aggregate size. So it's got that 4.75, we have a 9.0, 9.5, all the way down to a 25.0. Again, if we go backwards, 25.0 millimeters, again, this is in metric. So remember that 25.0 is actually about 1 inch. So 19 is about 3/4 of an inch, 12.5 millimeters is about 1/2 of an inch, and 9.5 millimeters is about 3/8 of an inch. That Z designates either the binder type, again that A, D, or E that we spoke of previously for our SUPERPAVE mixes, or the performance grade for SMA mixes or for specialty mixes. So let's go down this chart for our SUPERPAVE mixes. We just talked about those types of binder grades, the performance graded asphalts that are used in all of our different mixes. You see on the mix type on the left side, we have mixes all the way from a 9.0A all the way down to that BM 25.D. And there's a chart here that tells you that for certain types of equivalent single axle load ranges, that tells you how much traffic is on that road, heavy traffic is on that road. And it ranges from all the way down at 0 to 3 easels. We're using that SM 9.5A. It's going to use a 64S-16, and again, that nominal maximum size aggregate is 3/8 of an inch. You carry that chart all the way down, and you'll see for our surface mixes, if you've got an SM 12.5E, that's when you have that equivalent single axle load ranges above 10. And then you have that performance grade, again, I spoke of earlier, of 64E-22, and it uses a nominal maximum size aggregate of 1/2 inch. So let's talk about our aggregates. Our aggregates are 94 to 96% of the total mix by weight, or 75 to 85% by volume. And again, those are primarily responsible for carrying the load of that pavement itself. So when the load is applied, the aggregates are what's carrying it. Those are interlocked together, they carry that load, the binder's holding it all together in a adhesive or a cohesive nature. Sources of aggregates, there are a number of sources for our aggregates. We can have pit aggregates that are naturally occurring. Those are basically dug out of a pit and then they're just sieved in the proper sizes. We have processed aggregates. Those are the natural stone that's been crushed and then screened. In the crushing operation, stone dust is also produced. And then lastly, we have our synthetic or artificial aggregates. Those are aggregates that are resulting from the modification of other materials, which involve both physical and chemical changes. So things such as blast furnace slag, that's the most common used artificial aggregate. And then in some instances, for certain types of our pavements, we even use what's called a lightweight aggregate. Those are our synthetic or our artificial aggregates. Aggregate characteristics. We talked about particle sizing. So now particle sizing and grading, that affects the stability of the mix, the void structure. We have to have a cleanliness of our mixes. Those need to be clean so that we get a good bond with our binders. And we have to have toughness and hardness, and then we need soundness. Soundness is that ability for it not to break down under traffic. We also have particle shape. Obviously, particle shape is critical that you get that proper interlocking of our aggregates. We have surface texture. We need that texture in our aggregates so that we get a good bond with our binder to our aggregates. You want to have a very good texture for those to hold together. That texture also helps with that interlocking. We have to have proper amount of absorption. The amount of binder that's absorbed in that aggregate is your absorption, and you need a certain amount so that you again get a good bond, but you don't want too much so that that aggregate is absorbing way too much of that liquid asphalt. And then binder affinity. Our aggregates are all either hydrophobic or hydrophilic, and that determines the stripping potential in the presence of water. So when our aggregates are in presence of water and freeze-thaw cycles, you don't want them to strip that binder off of the aggregates. So we need to be sure that we get that. In Virginia, they use chemical anti-strip additives as well as hydrated lime. Polishing. Under traffic, the surface texture is smooth or loses friction or skid resistance. When our aggregates polish, they tend to get smooth, and therefore you're not going to have that skid resistance you need for safe travel of our traveling public. Limestone or aggregates that are high in calcium amounts, they tend to polish under traffic. For that reason, they're typically used in our intermediate mixes and our base mixes. Granites, trap rocks, diabases, and other aggregates that have silica, that are silicious, they tend not to polish. So we use those in our surface mixes so that we maintain that skid resistance that we need in our pavement structures. So now, some of the physical characteristics that are determined by testing. Things such as voids in the total mixture, VTM, voids in the mineral aggregate, VMA, voids filled with asphalt, which is your VFA, and then we also have fines to asphalt ratio. Here's a chart that's in our VDOT specifications, and it actually talks about each and every one of our mixes from our SM 9.5A all the way down to our BM 25.0. If you look for VTM in production, you got a 2% to 5%. So a SM 9.5A would use 2%, would require 2% to 5% VTM. For VFA, it's 75 to 80 in design, and it's 70 to 85 in production. Our VMA, minimum VMA is 16, and our fines to asphalt ratio is 0.7 to 1.3. All of these with a 50 gyration level. So this chart gives you all the breakdown of the various volumetric specifications for each and every one of the mixes. So let's talk about for a minute the voids in the total mixture, or the VTM. That refers to the small air spaces or pockets of air that remain between the coated particles and the final compacted mixture. Recognize this is that final compacted mixture. You want to know how much air is in there once it's compacted. Air voids are necessary in a dense graded highway mix to allow for additional pavement compaction under traffic. So you want to be sure, because if you get them completely filled and then you have traffic applying loading onto the pavement, then that liquid asphalt has nowhere to go and you're going to have flushing or rutting. So in most instances, you have to have in the laboratory a VTM range from 2 to 5%, but in the roadway we need a VTM range from 5 to 7.5, recognizing that the compaction levels that you get in the lab and that gyratory compactor are different than what you really get in the roadway. So the roadway requirements for VTM is 5 to 7.5. The durability of asphalt pavement is highly dependent on the air void content. So think about it. Air voids can be either too low or too high. Low air void decreases the permeability, which keeps the water out and reduces the oxidation. That's what you want. You want to try to keep that permeability low and keep the oxidation levels down. However, if it's too low, again, like I talked about a minute ago, where you get close to where you've filled all those air voids up, then the flushing of the binder to the surface can occur under traffic, and then you get a slick condition and the pavement becomes unstable. Density and air voids are inversely related. So the higher the density, the lower the air void. So if you have 6% air voids, then you have 94% density. So let's look at those air voids. So sometimes it helps to see a visual image of it. So if you look at this image on the far left of a compacted asphalt specimen, you can see the white spaces. Those are the air voids. There's the air voids that are in your mixture. Some of them interconnected, some of them are not. So as you take those air voids out and you move across, you see the mix with the asphalt removed, and that's all air voids. So in this case, the air voids, again, are that space that's not filled with anything except air. Voids in the mineral aggregate. That's the air void space that exists between the aggregate particles and the compacted mixture with the asphalt binder removed. So the VMA is that all that space in the aggregate with that binder removed. So now you have your VTM that you had, your air voids, and you take the binder out, and what's left is that aggregate, and that's that space. That's the VMA. So VMA represents the space available to accommodate both the asphalt binder and those air voids. So you need to have a certain amount of VMA so that you can ensure you have enough space for your binder and the air voids. The higher the VMA, the more space you have available in your asphalt, which increases the mixture durability. So a higher VMA produces typically a more durable mix. So a minimum VMA requirement, if you go back to that specification chart we talked about earlier, the specs require a minimum VMA to ensure that we get that durability. So let's look at this chart real quick. If you look on the middle specimen, you see the mixed specimen with the air removed. That's all just the aggregates that are left. So all that space that's there, all the white space in your middle one, that's all VMA. So all that white space again is VMA because all you have there is your aggregates and then the airspace. If you look on the right, you'll see that VMA again, the voids in the middle aggregate, is that space that was occupied by the air voids and your liquid asphalt binder. So let's talk about voids filled with asphalt now. That's the percentage of voids in the compacted aggregate mass, or that VMA, that are filled with the asphalt binder. VMA is important not only as a measure of relative durability, but also because there's an excellent correlation between it and the percent density. So you need to have the proper VMA to get the relative durability that you want in your mixtures. So if you have a VMA that's too low, there's not enough asphalt binder to provide that durability, and the mix will be prone to fatigue. If you have a VFA that's too high, then the available VMA has been overfilled with asphalt, and the mix will be prone to overdensification under traffic and lose stability. So again, if you go back and look at our charts, you see that the VFA is also represented here by that air void space and the liquid asphalt. So FA ratio. FA ratio is an indication of the asphalt binder film thickness of the coated particles. Film thickness on our aggregates is critical to ensuring that we get a good durable pavement structure. It's the best way to get a relative measure of that is with this fines to asphalt ratio. So that binder film thickness helps reduce premature aging and moisture damage. And it can also, like I said, be a measure of the coating by the binder. And it's very easy to calculate. It's just the percent passing the number 200 sieve divided by the effective binder content. And again, the effective binder content is the total binder subtracting out the amount of binder that was actually absorbed in the aggregate. So some other important properties. You have that percent binder. You need that to calculate all your volumetrics. So you have to have the percent binder of your mix. You have to have the total, the effective percent binder. That's needed to calculate the volumetrics. Again, the effective binder being the binder that is not absorbed in the aggregates. You need your mixture gravities, and that is the mixture itself as well as the actual gravity of the aggregate. So you got to be able to get all the mixture gravities. You need the tensile strength ratio. Tensile strength ratio is used to determine the stripping susceptibility of the actual mix that you've produced, and it has to be 80 or above. And then you have surface mix permeability. So that percent binder, that's the portion of the binder, again, that is critical and must be accurately determined in the laboratory and precisely controlled on the job. The optimum binder of the mix is highly dependent upon those aggregate characteristics we talked about, such as the gradation and the absorption. And the finer the gradation, the higher the amount of surface area. So if you think about The smaller the aggregate, you'll have more aggregate in a given volume, so therefore you'll have a higher surface area, so therefore you'll have a greater amount of binder required. So the finer the aggregate, so a 9.5 mix is going to have more binder than a 12.5 mix. And the higher the aggregate absorption, the greater amount of binder that's required. So again, we talked about a minute ago the percent binder that's effective. That's the total asphalt binder. That's the amount of binder that must be added to the mixture to produce the desired mix qualities. It's the amount of binder that's not absorbed by the aggregate. We've talked about that numerous times now. So keep in mind that the effective binder is that binder that's not absorbed by the aggregate. So it's the amount that effectively forms that bonding film. So again, we want to try to be sure that we're taking into account that bonding film that's around our aggregate surfaces. It fills the void space between the aggregate particles within the compacted mixture. And it's calculated simply by subtracting the amount of absorbed binder from the total binder content. So that's P sub BE minus the total percent binder minus the binder absorbed. Mixture gravities, we have Gmb and Gmm. The bulk specific gravity, which is the Gmb, refers to the relative specific gravity of compacted asphalt mixture as compared to that of water. So keep in mind that this is what you're comparing that to water. Weight of water is 62.4, so you're comparing that mixture to the weight of water. The maximum specific gravity Gmm, or otherwise known as RICE, refers to the relative specific gravity of an asphalt mixture at a theoretical maximum. So with that, the absolute maximum zero air void space is compared again to water. So now you have a mixture that has zero air voids in it. It's all aggregates with no void space, aggregates and asphalt with no void space. That's the maximum that mixture can possibly achieve. Water is at 77 degrees, has a specific gravity of 1 gram per cubic centimeter. That's used in all of our calculations. Liquid asphalt has a specific gravity of, say, 1.07. That obviously varies a little bit from binder manufacturer to binder manufacturer. Everything's compared back to water here. So a typical mixture values that are dependent on, obviously, your aggregate gravities. So a typical bulk specific gravity might be between 2.3 and 2.5. A typical maximum specific gravity is obviously going to be a little higher than that. It's going to be 2.4 to 2.6. So always keep in mind your GMB or your bulk specific gravity has to be less than your maximum specific gravity. So if you're running a test and for some reason that your bulk specific gravity is higher than your maximum specific gravity, then you've done something wrong. You've either done something wrong calculating your bulk specific gravity or your maximum specific gravity, and you need to go back and check that. Tensile strength ratio. Tensile strength ratio is the measure of strength loss resulting from the damage caused by stripping under laboratory controlled accelerated freeze-thaw conditioning. So obviously our pavements have a certain amount of damage over time. So what you're trying to do is replicate that in an accelerated condition to see what level of stripping is occurring at a specific pavement. Those results are used to predict long-term susceptibility to stripping in your asphalt concrete mixture. And to combat that, the effects of water damage and anti-strip additives are used in all asphalt mixes. VDOT requires anti-strip additives, whether it be a chemical additive or a lime, in all of their mixes. And they use that as an insurance policy. But your mixture itself has to be an 80 or above TSR. So it's 80%. So it has to meet that plus use either a chemical additive or 1% hydrated lime. Surface mix permeability. The test provides an indication of the water permeability of a water-saturated sample compacted mix. So that sample is completely saturated. It's a measure of how easily the water will be able to move through the void structure of the mixture while placed under traffic. So you want to determine how quickly that water will actually pass through a specific asphalt mixture. And it's an indication, obviously, of the interconnectivity of those air voids in that mixture. So if the air voids are not connected, then the water will not pass through it very rapidly. If the voids are connected, then the water will rapidly pass through that mixture. So that's it for this module. If you have any questions, please ask your facilitator. You have some knowledge checks at the end of the chapter. Go through those to help determine whether or not you understand this material.